I'm very grateful for the invitation to this meeting. Okay, maybe I start first with a motivation for this particular topic. So, in the recent few years, one of the member of our small team is here, David Gelbwasser. We have also in our small team one of my PhD students and Alejandro Genki. So we are working, we are trying to understand how the standard devices which transfer energy into work, like photovoltaic cells, thermoelectric cells, fuel cells, but also biological engines work. And when we started to search in the literature, it was a bit a shock for us that we do not understand at all what is the standard description of these devices. So, first of all, you see how does the standard picture looks like. So we have something, the engine itself is essentially always interface between two materials. So in all this example, we have the same scheme. We have either p-n junction, also an organic solar cell. We could have metal-metal junction for thermoelectric cells, electrolyte junction, and also biological membranes. We have also a gradient, which could be, this is the source of energy for this engine, and this gradient could be a gradient of temperature or chemical potential. Sometimes you can even exchange, it depends on the theoretical model. You can replace gradient of temperature by chemical potentials. And what is produced, what is the output of this engine, is a DC direct current which flows in a closed loop. On the other hand, one assumes that this transformation of energy from, say, the environment to heat or chemical source is direct and stationary. There is no time dependence in the standard theory of these devices. But of course, if you think about the current flowing in a closed circuit, it cannot work like this. We have at least two basic physical laws which are violated by this scheme. So first one is the Faraday law. To have some electromotive force, you need this integral over closed path to be non-zero. So on the other hand, from Faraday law, it means that you have time derivative of magnetic flux constant. So it means that magnetic field grows into infinity. So it doesn't make any sense. But you have also the even more general argument based on the second law. If you think about engine in terms of working fluid and you consider a piece of this working fluid, then you have the relation between a mechanical work output, between absorbed heat, change in the quantity of matter. You can have many elements, many substances, but I use only one. And the standard formulation of the first law, which is conservation of energy, essentially. And moreover, you know that if the engine should work permanently, you need a kind of cycles. It can be, in principle, infinite cycles, but after completing a cycle, the internal energy of the working substance should return to its initial value, and also the quantity of this substance should be the same after completion of the cycle. And if you put all these bounds and you add positive entropy generation during the cycle, you can get the following formula. It is already the 19th century formula, maybe slightly modified. duet relay, when you see that there is a bound on work, where Td is a difference between the temporal temperature and the average in time temperature. So you see that the work can be positive only if at least one of these variables, temperature or chemical potential, vary during the cycle. So it cannot be a steady state description in this picture. You need really a non-trivial cycle during the cycle something must change in the system. Okay, there's quite a large literature on this topic, and there are many models which, in my opinion, are not correct or inconsistent. So the first model, quite often used to describe solar cells, photosynthetic systems, and also biological engines, is based on this work depository as a kind of the sink, so the low-lying level of some physical system. And this is used to, the energy transformed to this low-lying level is assumed to be work. But again, this is highly inconsistent with the second law of thermodynamics. So simply if you calculate entropy balance and so on, you see that the relaxation to low-lying states means that there is a large entropy transfer to this state. Because such low-lying state, because it's essentially equivalent to a coupling to a cold bath at almost zero temperature. And in the formula for entropy exchange, you always divided heat by the temperature. So it's large entropy transfer in this model. But on the other hand, work is energy without entropy, essentially. So this is difference between work and heat. For work, we have energy amount with almost zero entropy. And this is nicely described in the paper of David and Alan, which is quoted here. There are also numerical examples for this. Another approach based on stochastic thermodynamics. Here we have roughly two standard models. First is cyclic non-equilibrium steady state. So then you have to introduce by hand non-conservative forces with negative frictions. Okay, one can use it as a kind of phenomenological approach, but there are no such forces in nature. And therefore, this model is rather unphysical, although we can reproduce the right results, but the price is too high. It's introduction of some unphysical element. There is another approach based on stochastic pumps. So driving of the current in a closed loop is due to periodic perturbation. This is much closer to the idea I would like to present, but what is still lacking in this approach is this feedback mechanism which generates this oscillation. These oscillations are put from outside somehow. What is interesting that essentially these two approaches are mathematically equivalent. When you average over this periodic modulation, then you can get the same result as for cyclic non-equilibrium steady state. So this is a paper with Chris as a co-author which explains this equivalence. Okay, so what is the picture I would like to advocate? So this is the picture of a quantum heat engine. It consists of several elements. Then we need some kind of working medium coupled to stationary non-equilibrium environment. We have this non-equilibrium environment. Typically, there are at least two heat baths at different temperatures, but they can be also a collection of chemical baths with different chemical potential. The third element is what is called work reservoir, work repository, or simply a piston. So this is the system which is essentially very simple. It should be, in most cases, it can be a single degree of freedom, and even harmonic oscillator is the most standard model for the system. And this piston exchanges energy with a working medium. And of course, the condition to have a really work repository is that there is a very small transfer of entropy, or small in comparison to other things. So we need energy transfer with small transfer entropy. And then we need also the mechanism to make the system self-consistent. We need a mechanism of self-oscillation. So the energy from reservoirs should produce self-oscillation of this piston. Okay, so now what is also important is the problem of definition of basic quantities like work and heat. I already said that work is something, is energy at zero entropy. So this could be a guiding postulate. So the question is, if you have a model with such a quantum piston, how can we compute the energy transferred to the system? So it seems that there is the method which is quite unique. It gives at least a unique result, and I think it's reasonable. One can argue that this is a right choice of the definition. It's based on the notion of passive states. These states were introduced in the 70s by mathematical physicists from Warsaw, and was known for quite a long time only to, say, mathematical physics community, but now they became much more popular, and also the, say, normal physicists apply this. Okay, what is the definition? So the definition produces the formula for work which can be stored in the quantum system and then extracted, by some other external devices. The name was given by ergotropy in the paper, I think, or Alaverdian and others. And the definition is the following. We take it's defined for the system in a given state and with a given Hamiltonian. So we first compute the energy in the state, and then we extract the energy which corresponds to the passive state, which is unitarily equivalent to ρ. So passive states are such states where the eigenvalues, so probabilities, are ordered in the decreasing order with increasing energy. From such state, you cannot extract energy by external Hamiltonian perturbation. So this seems to be a good definition of the work really accessible from the system. Okay, so now the model. This is a kind of quite radical simplification of the idea of it's chemical engine, but also can be applied to heat engine, but I will concentrate on a chemical engine case. So in this system we have the source of energy is a chemical reaction. Here I choose an example of the chemical reaction, but it can be even less complicated with only two components, A and C, for example, or can be much more complicated. It doesn't matter. It's important that we have certain reaction, chemical reaction, and we have this harmonic oscillator which is coupled to this reaction coordinate. in a sense. So X denotes excitation of the piston, which is here treated as harmonic oscillator. So there are natural examples of such a situation. Maybe the best known is a chemical laser working in a single radiation mode, and essentially all types of laser type models. When we have some well-defined radiation mode, but it can be also maybe for acoustic modes similar. And there is another example, what I called X plasmon. So this is exactly what we need to describe the piston in the case of photovoltaic cells, fuel cells, and also I believe in biological engine. It represents kind of collective, usually semi-classical oscillations of charges. They can be real plasma oscillation like in solid state physics, but it can be also phonons which are coherent on the relatively large space scale and which couple to electromagnetic radiation. So this is again quite large class of system. You see that in this model we do not have working fluid or working substance. We have directly the reservoir and the piston. It's only to simplify the model to produce in a clear way the final equation of motion for this piston, but somehow this working substance is hidden here in the reservoir, because a part of the reservoirs are really change states, but we do not see this in this global picture. So, okay, there's also the last example where this is a real chemical reaction, and this is a kind of molecule, which I called replicance molecule, because we will see that this model describes process of self-replication when we think about say, strictly chemical application. Okay, so now we come to the theoretical description of this model. So we have a Hamiltonian, which is a sum of Hamiltonian for the oscillator, for the piston, 3 Hamiltonians for reservoirs containing molecules of type ABC, and the interaction. The interaction is constructed in such a way that, for example, the second term describes the creation of X, of this phonon, say, of our oscillator, and R can be quite complicated operator, but generally it acts like annihilation operator for A and B and creation of C. So another term describes the reversed process. So one can think about this as products of creation and annihilation operators, but they are not necessary to be those operators for bosons and fermions. The computation below is essentially independent of the details of the model. It can be quite complicated situation. Only what we need to define the operators which counts the number of molecules of a given type. And moreover, we need also the commutation of this number operator with 3 Hamiltonian, what means that the reaction can take place only if the oscillator is coupled to this chemical bus. So we need to have this oscillator as a kind of intermediate agent which allows the chemical reaction. So to encode the structure of the reaction, one should imply the following commutation condition. So if you put here this creation annihilation operator as a kind of exercise, you will see that this is exactly what one should expect. So this is the condition which encodes the form of the chemical reaction. So now this is a standard picture, and we can apply the standard derivation of the Markovian master equation for this oscillator, for this quantum piston, and what we get, it's the most popular quantum master equation for the harmonic oscillator with damping and pumping terms, which can be calculated from the basic elements of the model, from the Fourier transform of correlation functions, but there are also another expressions, maybe more familiar, simply based on the Fermi-Golden rule. So if somebody prefers Fermi-Golden rule applied to the interaction Hamiltonian, it will give the same final formula. Again, from this very general structure, so without any additional assumption, one can derive the expression for the ratio of the pumping term to the damping terms, and we see that this is given in terms of Gibbs free energy released during reaction, where the quantum of this oscillator is treated as a kind of, say, molecule of the substance with chemical potential omega. So the sign of this delta G determines whether pumping dominates over damping, and we have some, say, explosion of the energy is transferred to the oscillator, or we have damping and nothing interesting happens. Okay, so under the condition of negative Gibbs energy, we interpret this that the reaction is spontaneous, and then pumping is higher than damping. And because this model is so simple, we can compute everything to the end, all interesting physical observables. For example, we can compute the energy of the oscillator, and it, in this case, grows exponentially. Also, the complex amplitude is amplified. So this is exactly what we expect from the model of laser, at least for under the condition that we do not reach some saturation regime, at least for short time behavior, such lasing system. So we have really an amplifier driven by a chemical reaction, and then we can also discuss two regimes, which depends essentially on the initial state, and I will say also that later it depends also, it can be modified by some additional decoherence effect. But under the spontaneous reaction condition, this oscillator is a work reservoir. So maybe I'll go first to the picture to see what happens. If we start with a coherent state, as an initial state for oscillator, it starts to follow, it still remains Gaussian state and follows the classical trajectory of, say, oscillator with amplified amplitude. So this is a spiral, and moreover, the width of this Gaussian state also grows exponentially, but one can compute now this ergotropy, so the part of energy which can be extracted from this piston as pure work. And you see that this difference can be, this ergotropy can be obtained very easy. We have to shift the true state to the origin and take the difference of energies between these two states. So then we get a really work admissible by some extraction procedure from the system. And we can also compute something more. We can compute the asymptotic efficiency of work storage. So it means that there's a ratio of this, say, work, this ergotropy, to the total energy. And it's always smaller, of course, than 1, but this constant is of the order 1 typically. So therefore, we may see that if alpha 0 is larger than 1, essentially larger than 1, then this efficiency is close to 100%. So the more semi-classical is the initial state, the more efficient is work storage in this system. So we need a condition for the self-oscillation regime that we are able to somehow initialize this piston in initial coherent state, which is somehow semi-classical. So, in the rather weak sense. Okay, so this is the efficiency. If the system works, if this piston works really in a semi-classical regime, so this initial amplitude is large enough, it can be replaced by time-dependent Hamiltonian. So this is how we can go from this self-consistent fully quantum model to the model with classical periodic modulation. This is also interesting to see where is the feedback in this scheme, because we expect from examples in physics, but also in technology, that for self-oscillations we need a kind of feedback. Here is something what I do not understand very well, because it seems that this is really a quantum effect, because probability of excitation is proportional also to the number of quanta which already are absorbed by the oscillator. So this is what in quantum in optics is stimulated emission effect. So it seems that it's somehow for this quantum model of oscillator is more or less automatic. You do not need to add some extra nonlinearities or something like that. So my question is how to explain this classically. Why in this case we do not need any extra construction. Okay, so we have this model which essentially describes the origin of self-oscillation in quantum piston. So it starts to oscillate with increasing amplitude, and then somehow this energy should be transferred, for some useful purposes. And this is a paper of Roney and others, a nice model of flywheel, quantum flywheel, which consists of measurement, feedback control, and external modulation. And it shows an example how one can proceed further with this energy stored in this quantum piston, quantum oscillator. Okay, so there is also a self-replication regime. One can notice that if we start with the initial Gibbs state, it remains Gibbs state with increasing temperature forever. So it means that if you start with a useless state from the point of view of work extraction, it remains useless. But this regime is somehow unstable, because if you somehow by chance create the amplitude, this amplitude starts also to increase exponentially, and then you can extract work. How can we stabilize this situation? It's not a good situation for engine, but it happens that it's stabilized. So the easiest way is to add pure decoherence, which doesn't change the energy of the system, but change the evolution of amplitude. This complex amplitude is damped. So if pure decoherence is large enough, dominates over this factor, then we do not observed, we cannot store work in the system, and essentially it doesn't make sense to describe this oscillator in terms of phase space as a kind of semi-classical object. In this case, we rather use the classical Markov equation for the probabilities, and we see here that this is, when we think in terms of the number of this quanta as a number of some molecules created in a fixed state, this is again a self-replication process because it's self-replication process because we have this probability transitions are proportional to the number of already created molecules. So this is another regime which perhaps can be applied to describe self-replication phenomena. Okay, so now some conclusions. So first of all, and this is somehow our mission to repeat that the present theory of this type of energy transducers like solar cells, thermoelectric generators, and other is not correct. It doesn't contradict the basic principles of physics, and therefore it must be replaced by new approach in which self-oscillations are played a very important role. One should mention also that one can have another class of models when instead of oscillator we have kind of rotator, so that would describe the situation of a turbine. But essentially, we didn't work on this, but probably the physics and mathematics is very similar. Then there is more fundamental question that somehow it's very difficult to describe work without some classical ingredient. In the definition of passivity, we have always this external Hamiltonian perturbation. And the model of flywheel is also a kind of external classical perturbation. So, okay, it seems to me that this problem to define work is a bit similar to the problem of quantum theory of measurements. And to avoid this infinite regression of measuring system, at certain moment we have to say, okay, this measuring apparatus is essentially classical. We describe it in classical terms. So this is probable. This is something very similar in the case of definition of work. We can have various definitions, but finally they become unified or unique in the semi-classical limit, where we go to the limit of classical system. This is probably because, as we say, the difference between work and heat depends also on the measurement procedures, on time, for example, which we can spend to measure system. Because it's a matter of making difference between systems which are random and deterministic. And sometimes we need time to recognize that some system which looks randomly are in fact deterministic. So this is, in my opinion, the source of this, say, never-ending discussion about the definition of work. Okay, so I think this is all what I wanted to say. Thank you very much for your attention.
I like your 79 paper, but I disagree with some points in your talk. Can we see slide 14? There you wrote the equation for
14, okay.
of a laser. That's
okay.
Yeah. And you indicate quite correctly that positive feedback is required.
Mm-hmm.
But that feedback comes into the gamma plus up and the gamma minus down. Mm-hmm. They have nonlinear denominators. And so the equation is something which has self-limiting features in it, and that's well known, not requiring a further analysis. Now, if we can go back to your last view graph,
to the
2 points. 3. First, as I said, I liked your paper, right? 79 paper. That's the first. Keep going.
You claim I should stop with this paper.
Let's see, a pointer. Well, here I have a question and a little problem.
Yeah.
The quantum theory of measurement, almost all problems are associated with off-diagonal elements of the density matrix. Some measure of coherence or entanglement is the essence of the difficulty. But in quantum thermodynamics, we're typically working with coarse-grained equations of motion, like the one you had on 14. So the off-diagonality is gone. And in that sense, the two are very different. What do you think about that?
Okay, I would disagree, because off-diagonality is very important in this picture, you know, of the semi-classical picture. So coherent states are highly off-diagonal. So only with this picture you can explain this difference between work and energy.
But go back to the laser. We know that in steady state, the laser equations in the number representation are diagonal, unlike a coherent state.
In the number representation, yes, this is a subtle point, because, you know, you can make also a mixture of coherent states over the face, and it looks diagonal. But, yes, this is a very good question. I don't understand this also completely, but to get the intuition of work, I need this classical picture, somehow.
We continue.
Your model is driven ultimately by this chemical reaction, A
Yes.
plus B goes to C plus X. So the exponentially growing energy, does that imply that this reaction is happening more and more rapidly at an exponentially growing?
Yes,
and
yes.
This is because of this, what did you call it?
This feedback, or here is essentially, yes, stimulated emission, yes.
Physically motivated? That seems a little bit odd.
I think in the beginning of the laser action, it's a quite good model. Then it's stabilized because of some nonlinear effects. Yes, would you agree? No? Okay.
That's fine.
But okay, this is a simple model, yes, to show this first, the origin of self-oscillation. Then, of course, many other things, you know, happens, and it's stabilized. So, first of all, you should extract this energy from the piston also to make some use of this.
Just a comment about your definition of work.
Yes.
So you used the ergotropy on.
Yes.
And I guess that two things. One is that you have other systems that you're using as well. You have these AC and working bodies and these various other systems. These ancillary systems you have that you're using as well. So it turns out that ergotropies, if you include these other systems, then in a cyclic process, then it turns out that a lot of states which you think you can't draw work for, you actually can draw work from. So I think you need to include somehow the other systems in the ergotropy in order to make it.
Okay, so
If you can have catalytic processes where you do a cyclic process, it's completely cyclic on the other systems, and yet you are able to extract. That quantity can change if you. It's not really stable under including other systems.
So maybe, but this is somehow, you know, the idea was to have the simplest possible this work depository. So and then this is somehow, in the end, is a kind of semi-classical system. So it means that it's quite stable. So of course there are some fluctuations, but I think this is somehow the essence of this useful work. I believe that this ergotropy gives quite a good approximation, up to some, of course. As you said, that there can be some fluctuations around, but in the semi-classical limit, I would say it gives the main contribution to work. So.
I mean, it also may be where you find the classicality comes in, because you're defining it with respect to a particular operator H. So if I were to just look at the change in the work system, that's a purely quantum thing. When I now compute the average energy, then that's like a measurement in some sense. That's really in some sense the classicality, I suppose.
Yes, yes. So the input of classicality is here, I think, in this picture essentially again. So that despite this, fluctuation and increase of the width, you still have something what is, say, well defined and can be extracted by external time-dependent Hamiltonian from the system, like in the definition of passivity. So this definition is, I would say, somehow stable, yes, in a sense. So I do.
Well, except that all passive states, if I add in another system, then they're not stable. So if I add in another catalyst, then I can extract work from the passive state, unless it's the Gibbs.
Yes, but probably you can think about them as a new bus, yes, and then things change, yes. So. Okay.
So, first of all, I think this is a very good start for our meeting. We should start with disagreement, and then maybe eventually we'll reach more disagreements, because this makes the field alive. So, thank you, Robert, again.